Okay, started. So I guess we're good to go. Everyone's here.
Let's do it. George.
Sure. Yeah, so the goal of this talk is to give an overview of what XLA GPU is and all the different ways we are trying to evolve it. So I guess it would be of most interest to people who are either working on XLA GPU, trying to extend it, or trying to build something similar, or are just looking for different optimizations which could be of use. And let's try to keep it interactive. There are many different subcomponents in the talk, so you can ask questions about any subcomponent. And if we don't go through all sections, I think it's fine. It's like better to cover less sections and more devs. Maybe I'll give a minute for people to join because there are a couple of... maybe it's fine. Okay. Yes, it was... Oh, well, maybe not yet. 30 seconds.
I will keep clicking it, mid.
Okay, you'll click it. Okay, so this talk is about XLA GPU with primary emphasis of NVIDIA GPUs because that's what we are focused on optimizing right now. And I guess you've had a lot of talks about XLA by now, but basically you have lots of frameworks which allow you to write NumPy-like code. You have stable echelon PGRT with your API, and then inside OpenXLA magic happens, and you can suddenly run that code at top performance on different accelerators. And we'll just go through different components of the compiler, and we'll try to cover in some detail what these components are doing and what are we doing with those components. So that's the diagram I'll use throughout this talk, and then we'll try to cover different boxes. But basically, yeah, we have stable echelon at the top, which is main IR we use as an input. We have PGRT layer as the bottom, which is the API, how different frameworks can interface with the compiler. And then the IR goes through a bunch of passes. At the end of the day, we fuse things, which is how we get most performance. And then there are a couple of codegen mechanisms. We were recently mostly focusing on using Triton as a codegen backend, but we have some generators which generate LLVM directly, that generates PTX. PTX goes through PTX-IS, and finally the resulting CUDA binary is launched by runtime. Not all HLOs go through the codegen. Some are lowered to the cuDNN and cuBLAS and various NVIDIA libraries APIs directly, and then the runtime makes those calls, and the runtime can communicate with CUDA APIs as well. These components do share code across backends, but they share it somewhat with an asterisk. So like usually there is a parent class, which is common across different backends. And then once we start optimizing for performance, different changes are necessary. And then backend specific logic starts to creep in essentially almost all of those layers. So PGRT, we will not cover pretty much at all at this layer, but basically it's a stable runtime API frameworks can use to interact. Oh, another one. Then we have stable echelon as a compiler input, which is a stable offset defined in the IR, which is with a specification and the community governance, which you could use to use XLA compiler and store the serialized IR on disk as well. So for instance, if we start this model on the Injax on the left, we get the IR and stable echelon on the right. And for historical reasons, the IR used inside is not stable echelon, it's just echelon. Well, in most passes inside XLA, but it's basically one-to-one. But in the rest of the slides, the echelon examples would be used. All right, so the first interesting component here is this PMD partitioner. I think it could be interesting to folks from NVIDIA that basically users can write programs which are larger than what can fit on a single device. You can imagine you can move around tensors of the size of, I guess, maybe not petabytes, but terabytes. And then you can annotate them with some sharding notations, and the SPMD partitioner will partition the code for you to run on different devices and insert the collectives for you as well. And that portion of the compiler is mostly backend agnostic. So that's roughly how the picture looks like. Researchers write model code where they pretend not to care that tensors don't actually fit on a single device. Then the annotations have to be inserted, specifying how sharding actually is meant to be in practice. And then the SPMD partitioner kicks in. It propagates the sharding annotations through the graph, because annotating every single operation is quite tiresome. So users will mainly annotate a few and rely on the SPMD partitioner to infer the rest. And at the end of the day, the partition per device graph is launched, which has collectives. And since it's a SPMD mode, each device will be running the same operation. So let's look at some example. Like, let's say we have a simple operation which has a matmul, which is multiplied by some constant and negated, and then we just return it. And let's say we want to partition that matmul across two different CPUs, and we define our axis in one-dimensional way. We just say that, well, we have a two-dimensional mesh, but the one dimension is of size 1, another dimension is of size 2. So the partitioning is fairly simple. Right, yes, so we define the mesh, we define the operation, and we define that we want to specify the sharding constraints on the output tensor. And we can look into how IR looks like. And then the IR for the input, unsurprisingly, looks very similar to JAX. You have a sharding annotation represented the custom call, essentially as a mechanism to pull it through. And then after the SPMD partitioner kicks in, it looks a bit more interesting. So now we have an all reduce operation. We have the ID. Well, and replica ID mostly, again, for historical reasons, but it's just basically identifying the partition we are in. And that identifies which part of the input should the given replica read. And then two different parts are computed in parallel and then joined with a reduction later on. So there are works to evolve the SPMD partitioner. We do hear various complaints that the different specifications for how operations should not be sharded are not well specified, and it's mostly a collection of custom calls a few people understand. So the goal is to have a spec implementation. Potentially, it could be componentized and outside of the XLA compiler, stable HLO pure transformation. And then a bunch of SPMD optimizations are also in development. Are there any questions on SPMD partitioner? I mean, I'm not sure if I can answer them, but I can do my best.
Yeah, one basic question is, how did you visualize this graph? Is there a way to emit this?
Great question. So HLO comes with a graph with visualizer, which is extremely useful. You can, I guess I'm thinking of what is the easiest way to do it. The easiest way, I guess, is if when you run operations through XLA, XLA has flags, which are specified using the XLA flags environment variable. And that has a dumping flag, which is -XLA dump2. And it has an options graph, which says dump graphs as graph is. And then it can not only dump the input IR and result in IR, but it can also dump all the intermediate states. And you can also specify both intermediate states. And then if you look at the XLA proto file inside the XLA codebase, you can see all the options it supports.
I see. Thanks.
Anything else? Should we go on? Okay. So algebraic rewrites is a fairly simple layer. So it basically performs HLO rewrites to make the HLO more canonicalized and to simplify different, sometimes superfluous operations like redundant casts. And we simply add more rewrites and more canonicalizations to that layer. Layout assignment is a bit more interesting. So the HLO has different representations for physical layout, which is how the tensor is actually stored, and the logical shape. And then that allows it to tune the physical layout separately from the logical shape. And that in turn enables a selection of optimal layouts for compute-intensive operations such as convolutions and matmals. And then once those layouts are fixed, they get propagated through the graph. And then basically if they're propagated both up to users, both down to users and both up to producers. And when two incompatible layouts are encountered, they like a physical transposition is inserted. So that's an illustration in how that's represented. It's very flexible, but also makes physical operations sometimes very hard to reason about. But basically for a 64 by 32 representation, there is quite a lot of, for a 64 by 32 matrix in HLO, there are multiple ways we could write it down. We could write down the logical shape as 64 by 32, and there are two different options for the layout. Or we can sometimes transpose the logical shape instead. And then there are also, it's meant to be 0, 1, two options for the layout. And that is, while flexible, creates some redundancy in representation as basically permutation over the logical shape, and permutation inside the layout could mean the same thing. And then you have two different representations for the same tensor, which isn't great for doing pattern matching and further optimizations, or just lowering from the HLO. So let's look at the example here. So you have two matmals going from int 8 and int 8 to int 32. And then in this case, it is convenient to store right-hand side in non-default layout, which is specified here as 0, 1. And then the advantage of the layout assignment pass is it can propagate that layout through the graph. And then we only need a transpose once on the second parameter of the fusion. So if we were doing a naive approach instead, where we would just insert the transpose when we need an operation, one sec, then we would have ended up with two transpositions. Yes, Kai?
We have a question here from the room.
So just sorry to jump back, but to the example before where we were talking about transposes, is the thing to see that tells you, oh, there's a physical transpose happening when the dimension numbers change, but the shape of the matrix is not being, that's not mirrored or something like this? Like what's the shorthand to go, oh, a physical transpose has been inserted?
Oh, okay, yes, thanks. So that's a good question, because it goes directly to the next interesting point about layout assignments. The consequence of the layout assignment pass is that user inserted transpose is actually ignored. They are more taken as a hint to the layout assignment engine, which tries to propagate it. And then the thing to look out for is a copy operation. So it's not exposed as the input IR. So there is like a bunch of HLOs which the user cannot create directly, and they can only appear from inside the compiler, and copy is one of them. But basically, after the layout assignment, transpose is essentially a bitcast, and copy is actual physical transpose, which performs a data movement.
They're the evil things to watch out for.
Yes.
Thank you.
Any other questions? Okay. Yeah, so that's pretty much just a visualization of the previous slide, that the layout assignment operation has finished. It has decided, it has fixed the physical layouts of all tensors, and it has decided where to insert the physical transpositions. So that approach is also sometimes not great, because sometimes users do want to actually control the exact layout, and we still work on the IR, which would enable doing that. And then, actually, funny enough, we have a pass which attempts to undo that representation duality, that the same shape could be represented twice with different ways, but would actually mean the same thing. And then we have a separate layout normalization pass, which attempts to put everything into the same physical layout. So just make it a descending layout, which is pretty much the default. And then instead of having a separate physical layout, just apply that permutation to the logical shape instead. So basically here it would be turning the right-hand side into the left-hand side. And the way it works is it starts with normalized islands in the HLO graph, and then it sets the bitcast, and then those islands grow outwards until they consume most of the graph. And actually, when we implemented that, we were quite surprised to realize it actually gave a rather sizable performance boost as well on a set of benchmarks we looked at, because all the different bitcasts in HLO are often not free, as they cost quite a bit of index computations. And often those bitcasts end up doing silly things like converting between two redundant representations, or adding and removing degenerate dimensions is another one example. And then getting it all into a normalized form where there are basically less possible shapes helps a lot to minimize the number of bitcasts in the graph. And then, of course, it makes it easier to lower the graph and to optimize the graph and to understand the graph for humans as well. For the evolution part, it's not that much. We're still working for auto-tuning for best layouts. So as we started to generate MetMults ourselves, the layout choice does matter there. We don't always know which layout is the best one, so we're still playing with different strategies, and we plan to extend layout normalization for all instructions. It currently covers most of the HLOs, but not 100%. And then, of course, I think that from NVIDIA there was a question a couple of times when users actually do want to enforce the layout, how to do that, since for now it's just advice to the compiler, but it would be great if users could actually force their will as well. Okay, so now let's talk about Fusion. So it's one of the most impactful optimizations in the XLA compiler, basically being able to take a group of HLOs and turn it into a single CUDA kernel, which greatly minimizes amount of intermediate memory traffic and improves performance. And then once those fusions are formed, the execution strategy for each fusion is chosen, which could be either sending this call to the library, or using the Triton cogen, or just lowering it to LLVM directly. So I guess everyone in the room probably knows what Fusion is, but I'll just have a one slide overview anyway, that if you have two kernels, such as multiplication followed by addition, and you are throughput bound, it's incredibly expensive to write the result to intermediate memory first, and then only to read it, as modern GPUs often have significantly more compute than they have bandwidth. And if we are able to just pass the intermediate result directly, either in shared memory or in registers, we can perform the computation twice as fast. Well, actually, it's even more than that. Like if you remain throughput bound, then all the fusions are free as long as the size of your fusion boundary, which is basically the amount of memory read and write and written, is the same, then you can fuse as much as you want. The fusions are represented as boxes when you are visualizing the HLO graph. And the way to read them is only boxes on the boundary of the large box exist in device memory. Everything inside is passed through registers or through shared memory. They're never materialized. And the whole box is generated to a single CUDA kernel. Well, it could be a library call, but we assume it's also a CUDA kernel at the end of the day. So for the fusion algorithm, there is a simple visualization here, which is incidentally also a tool inside XLA you could use to try to understand what fusions are and how they work. It's one of the damping options present in the compiler, but it works as this local fixed point algorithm where it starts with a fusion and then iteratively considers different producers going into it, and as long as the constraints of a single kernel satisfied, such as we don't exceed the amount of shared memory we have, or we don't exceed the number of registers we have, and ideally, as long as we don't increase the fusion boundary too much, then we perform this fusion, and then we iteratively grow these clusters. And of course, since it's a local greedy approach, it sometimes leads to unoptimal decisions. But in the evolution section, I'll cover how do we plan to overcome those. So any questions on fusion so far? No, okay.
Oh, we had a question.
Okay.
So you said that fusion could be detrimental in terms of performance sometimes.
Yes, of course.
Is there any way to unfuse it later on? And do you do any kind of rollback?
So no, we don't actually have a way to unfuse it later on. We have evolution plans which aim to overcome it by taking more informed local decisions. But basically, it's an NP-hard problem, at least, right, to find an optimal fusion boundaries. So I think we have to content ourselves to finding the best local mean which we can find. And it's not feasible to just try all the different possible fusion boundaries and choose the best.
Do you have an example where we fuse and we have more information later in the compiler, which might suggest we should unfuse something? I guess the question is that, why can't we, whatever later in the compiler information that you have could, I guess the strategy is to just make the initial fusion decisions correct, so to speak.
The strategy is to make initial fusion decisions correct. Sorry, could you restate the question?
It's not a question, it's a comment. I guess what I was saying is that are there cases where we fuse something, but then later on in the compiler, we know something that sort of suggests that we should unfuse that fusion.
Oh, I think.
What I was saying was that our strategy is to make the initial fusion decision right, and we don't have to unfuse it again.
Yeah, I don't think we know that in the compiler. I think we just look at the fusion and we're like, oh, that's slow. We shouldn't have fused it. At least the way we recognize them now is mostly based just by human analysis. We do have a primitive cost model for fusions, which we are working hard on expanding right now and generalizing further. So this gives an example of where you do need some kind of a cost model. So as mentioned before, GPU kernels are mostly throughput bound from the ones we see, unless like it's a large math-mal or a convolution. And then the corollary is compute comes for free. But then it comes for free until it doesn't. So if you do have such a large tower of logs, then, oh, and you have like a broadcast at the bottom, then you can fuse more and more. But as you fuse, that entails log recomputation. So if we just, if we were just to cut the fusion here, we would only calculate, sorry?
Go ahead, Sean.
Just the sneeze, sorry.
Okay. Yeah, and then depending on the different dotted lines, there are different layers of recomputation we could have. So like if we cut it here, we only recompute log, but if we cut it here, we recompute log. And if we cut it here, it will be recomputing log. And as you increase that tower of logs, at some point you run out of compute, and then fusing further is not helpful. So that's an example where we are using a cost model to estimate a compute operation, a compute cost of an operation, and to prevent fusing operations which actually makes the whole thing slower, not faster. And that's an example of a non-locality problem in fusions, where in the previous example, I said that like we take all these decisions locally, and let's say we have some fusion box at the bottom, and we have an addition kernel at the top. So that's a binary operation, right? So that would increase, if you were to fuse the addition, that essentially doubles the surface area of the fusion. And that actually causes us to read a lot more, well, twice as much memory than we would have read otherwise. So just by looking at the addition operation locally, a tempting answer is to say, no, we cannot fuse it because we don't want to double the surface area. But then it becomes complicated, because if we do fuse the whole region all the way through, there is a parameter at the top, right? So in that case, we do want to fuse it. But it seems very tricky, because we don't undo the fusions, as otherwise we would run into this exponential backtracking problem. Right, yeah, so if you do that, it goes from 400 to 800 bytes, but if you fuse the whole thing, then that's the best. And the solution we have under development so far, I think it's upstream as well, but not enabled by default, is to have a priority queue-based fusion guided by a cost model, which would actually use things first, which are beneficial to the fusion. So in this case, I think it will fuse broadcast first and into addition, and then only fuse the whole thing into kernel. So that gives us a trick where decisions remain local, but because the order in which they are considered is influenced by the shape and by how beneficial those fusions are, it often does yield a globally optimal solution, even though it's a non-tractable problem in general, and I don't think the priority fusion guarantees it. Right, so the evolution plan is to launch this unified priority queue-based fusion where it's guided by a cost model. Right now, it's a bit hacky. We have multiple fusion passes. Some fusion passes query the cost model, some do not. And if we could land it, it would give rather considerable performance gains on the set of benchmarks we are looking at. Any other questions on fusion or priority queues?
One question.
Right now, about the broadcast, you suppose that you will recompute the computation for each load. In theory, we could modify the code gen to load the data only once per block and reuse it. So there's a middle ground between the two extremes. Did you investigate that?
You're talking about this example where you could still alter the code gen and fuse the tower, not cut it, but still get the optimal performance.
Uh,
Or
No,
you
I-
just in general?
I mean here, not, yeah. Let's go that offline. I'm not able to explain it shortly.
Okay. But I think the answer to your question would be that maybe in this case, but in general, you do run into compute limitations where the best answer is to cut the fusions. And I don't think all of those are solvable with better code gen. Another interesting box in the compiler is auto-tuning. So we love to have analytical models which can solve things deterministically, but unfortunately, it does not look always feasible, especially when we have MATMAL tiling problem with fusions which we generate, which will come to around later. So in this case, XLA chooses to auto-tune, which basically is as we compile many different configurations, we time them, and we pick the fastest. So that has a lot of disadvantages, that it becomes non-deterministic run-to-run, and it's quite expensive. But some choices just simply don't seem very tractable analytically, or we haven't developed a sufficiently complicated decision model yet. And the evolution plan is to try to develop a decision model to at least guide the auto-tuning to cut the number of configurations we have to consider. I guess another large disadvantage is it requires GPU during compilation, which isn't great. But then again, it doesn't look very tractable so far otherwise. And auto-tuning is heavily used for codegen for deciding, well, firstly, what do we send to libraries and what do we code generate and which codegen paths do we use. So here we use Triton mostly for doing MATMAL fusions for anything which ends into MATMAL, and sometimes even the MATMALs themselves. And the pure LVM codegen is used for reductions and for transposes. And basically, we have those are the emitters we had before Triton. The Triton emitter was only developed this year. And basically, there are only, like you could say, there are only 3 emitters. Well, there are more cases, but mostly it comes down to those 3. There is a generic loop emitter, which has a single function produce a given element at a given index, and then it propagates that recursively up the graph. So it can generate almost an arbitrarily complicated fusion, but it will not be very efficient because it doesn't vectorize, like it doesn't use shared memory, it doesn't guarantee coalescence, it relies on LVM for vectorization, but at the same time, the generality it maintains is quite high. Then we have 2 so-called hero emitters. They're called hero because we look at the root operation of the fusion. So if it's a reduction, it will go to the reduction emitter. If it's a MATMAL, it will go to the MATMAL emitter. And basically, the root operation of the fusion determines the codegen strategy for this fusion. Well, it's not always a root operation. You can still have an epilogue fusion, but it's like the main operation which determines the tiling strategy of the cluster. And then for the direct LVM emitters, the main 2 are reduction and transposition, and then they recursively call into the generic emitter for the prefix and the postfix of the computation. Then codegen to Triton IRA is what we've heavily focused on this year. So I guess probably everyone in the room knows Triton. It's a block-level programming language which allows to generate kernels with high performance based on a high-level IR than CUDA, where you just specify what each block is doing. You don't need to control different threads. You don't need to control shared memory. But at the same time, it yields very high performance. And XLA has a tiled emitter, which looks at different MetMal fusion configurations and then generates Triton IR from those HLO fusions, and which we use for MetMal fusions and for softmax. And yeah, that's like a graph of how MetMal in XLA look like, where you have left-hand side and right-hand side. And you have a loop which computes the MetMal. And the ways the Triton IR is emitted is we propagate the dimension analysis first. So I can't expand on it as it would take too much time, but basically we first start with a way to tile the root operation, which is a jam. There is a separate talk, by the way, on figuring out the tiling transposition. And then the tiling of the hero operation determines the tiling of all the prefix and the postfix. Then we propagate the tiling, and once tiling is propagated, we can convert HLO to Triton IR and then generate a high-performance fusion. And for that approach, we got quite a lot of success, so we could generate really quite complex fusions, and we were quite satisfied with performance. For the, at least on A100, for H100s, it's fast, but it doesn't seem to be that close to roofline. As to whether those fusions especially are super complex ones are close to roofline, it becomes very hard to tell, as we don't have a reference implementation we could compare to. And then we sometimes try to prototype something in Cutlass to compare, to figure out the difference between the possible roofline. But in general, they do seem to be quite fast. Right. And then for evolution plans, we plan to move more and more things towards Triton and to unify code generation there. And then to not be particularly rigid about it. So if there are approaches which are much faster than what we can achieve with Triton, then we would use them and use some kind of a cost model or auto-tuning strategy if it's not possible to determine analytically to pick the cogent provider for a given fusion. Any questions on the cogent? No. Okay. Okay. So once we form those fusion clusters, we need to figure out in which order to run them. So in XLA GPUs, the execution is fully serial, excluding collectives. Like collectives do have a hack which allows them to run separately on a different stream because there is like already use start and already use end. But apart from that, the execution is fully serial. So there is no interrupt concurrency, which is very different from TensorFlow. And then concurrency is instead achieved by fusing more things together. For example, like you could emulate interrupt concurrency by simply having more horizontal fusion. So that might not seem like a great decision because there are no different iterations running at the same time. But at the same time, we haven't really found that to be a limitation, and it makes for a deterministic, simple, and easy to reason about schedule, where in the profiler, the order of operations always looks the same run to run. But the scheduling in itself could be an interesting optimization problem. So if you consider a simple graph, like on the right, you have a bunch of broadcasts, you have a bunch of reductions, and then you add those reductions together. You could try for instance, to run all the broadcasts first, and then all the reductions, and then to add the reduction outputs together. But in this case, you would need to keep the outputs of all broadcasts alive at the same time, and that would waste 1.2 kilobytes of memory. So XLA uses a simple heuristic to determine the scheduling order when multiple operations can be scheduled at the same time and the order is not fixed, and which is a memory minimization by the sum of the freed memory minus the sum of allocated memory. So in this case, broadcasts allocate a lot and free very little, and reductions are the opposite. They allocate almost nothing, but they free a lot. So under the schedule, we try to always schedule reductions first whenever possible. And then if you schedule the computation as broadcast reduction, broadcast reduction, broadcast reduction, you only have a peak memory of 400 bytes, which is 3 times as better, 3 times as good as the previous approach. And another interesting scheduling problem, actually Rahul, who's in the room, can probably
Just a question on the previous George. You were saying that the reduction is freeing a lot. Like in practice, that assumes that the operands are not used elsewhere. Otherwise, in practice, like if you were moving a reduction very early, but the operand was used elsewhere, you would just actually increase the memory pressure as well, right? I guess it's fine here because those reductions are to scalar, so they don't actually allocate much. But in general, for an operation that still allocates less than it frees. I was trying to understand what you call free, right? It's a local property of the operation, just means.
Yeah, actually, I'm not sure I can answer straight away at this level of detail. So those computations are done on HLO values, not HLO instructions. I don't actually know if it's like the amount of memory is the value itself free. Maybe it takes all users. Maybe it actually takes all users at that level of detail. I don't know, to be honest.
Free is the volume of the operands of the operation?
No, I'm saying like this computation is done on a class called HLO value, which I think would take the usages into account. But honestly, I don't know if that is being taken into account during the computation.
All right, thanks.
I would think that, again, like it's probably not globally optimal and you can't guarantee optimality, so some shortcuts have to be taken, but I don't know if this particular one is considered. I think it is, from what I remember from the code, that it would actually say like when it frees, it means that no users are scheduled after it. Okay, and this one I'll just cover very briefly because I think it also deserves and probably has a separate talk in itself, that we overlap communication with compute. And there is a desire to hide communication as much as possible between the compute. And then a separate CUDA stream for collectives is done, and that requires either a profiling guided estimation for how much communication and computation takes to achieve the ideal overlap, which latency hiding scheduler is trying to do. Oh, sorry, no, so latency hiding scheduler is trying to do the analytical computation, but there is also a profile guided optimization, which will actually just take the measurements and do the best overlapping schedule. And the goal is to use a post model or either to use an auto-tuning based approach, so users don't have to store a profile and to load it separately in order to achieve great overlap. Yeah, and that is a very large focus for giving great training by default on with XLA, because for training, overlap of collectives and compute is one of the most important factors for performance. Okay. And once we did the scheduling computation, we have a separate stage called buffer assignment. So XLA doesn't call malloc during the execution. Everything is allocated upfront, and then it tries to minimize fragmentation, maximize buffer use in order to reduce the intermediate buffer as much as possible between all the different instructions. Basically, XLA has three kinds of buffers. There are input buffers, which are provided by the user. There is an output buffer, which could be either provided by the user or the one XLA allocates itself. And then there is a single intermediate buffer, which is for all the instructions which are not directly observable by the user as input or output. And then all these instructions get a slab inside the intermediate buffer. And then we can look at an example here where we have a single program on the right. There is no aliasing, and we have a single buffer associated with each instruction. So here we start by calculating live ranges first. So we have a broadcast, and the time is just elements basically when something becomes alive or something dies, we insert a new unit of time. And then we have this very simple stacking diagram of when new slabs appear, and then the box is cut when they die. And after those live ranges are calculated, XLA attempts to solve a minimization problem. Basically, that there is a y-axis is the number of allocated bytes first, and that essentially plays a game of Tetris where the x-axis of each instruction is fixed, so they're not changed from the previous picture, and the size of each buffer in y-axis is also fixed, so we cannot change how much instruction memory occupies. And then basically what we can change is the order in which they are dropped down. At least that's the way I think it's easy to visualize that. It's almost like playing Tetris with x-axis fixed. And that's essentially comes down to bin packing algorithm, which is again NP hard and not tractable in general. But the way it's solved is that different approaches are tried, and an approach which results in smallest high watermark is chosen. And by tried, I don't mean that like we actually try to allocate them. It can be all tried analytically, so those calculations are very fast. Yeah, sorry. So for the slides, the two approaches are we can try to minimize either the vertical size of the block, or we can try to minimize the horizontal size. So either to consider instructions first which are alive least amount of time, or consider instructions first which occupy least amount of space, and then try to schedule them in that order and to compare the high watermark of the occupied RAM, which is what we're trying to minimize. There is also a Shillori materialization pass on top, which basically does something like if you try the scheduling and you see that after your schedule you still occupy more memory than your GPU has, you can resort to recomputing some of the fusions and trading some compute for memory, which can often save you from if you are just under the limit, sorry, just above the limit. So that's the problem of trying to minimize bufferization, minimize the high watermark of memory is interesting because it's tightly coupled with fusions in a way and introduces a phase ordering problem. So normally we do fusions first, and then we do the buffer, then we do the buffer assignment. But if you fuse too much, that can force multiple different buffers to be alive at the same time, which need not be alive at the same time. And then ideally, it would be great if we could go back to the fusion decisions and say, okay, maybe let's not do such expensive multi-output fusions. Let's do something cheaper. Let's spend just a bit more compute and get more memory back instead. But this is not something what we are doing right now, and that's what we are considering. Any questions on buffer assignment?
This is one case where we can undo fusions.
Sorry?
I guess this is one case where we could undo fusions to get it back to.
Oh, yeah.
Just
Yes. So in this case, yes, but then it's the computational cost is somewhat unclear. But that is being considered. That maybe we could just redo the fusion pass and say, okay, let's ban all multi-output fusions because they tend to be expensive with respect to the high watermark for memory. Okay.
I just wonder, this fusion parts to minimize device memory is also considering the auto-tuning.
We don't have such a pass, like it's all just being considered right now.
So the auto-tuning is not considering about minimize the memory. It's only for the ops fusions.
Auto-tuning right now is only used for minimizing latency, so minimizing the runtime of different fusions, and is mostly used just for fixing the cogent strategy, right? So for instance, we may generate a matmal fusion, and then we have options. We can generate it using Triton, but then for Triton, we need to pick a tiling. So in this case, we auto-tune. Or we also have an option to give the matmal to kublas and to fuse the rest instead. And then, of course, you also, even if you do Triton, you have an option to do a split K matmal, in which case you generate an extra reduction, and then you also need to do something else with it. So for those options, we would auto-tune to pick the best one, but which I guess can affect your fusion decisions, but it's not like for the fusion itself, which we auto-tune.
Okay, thank you. Thank you.
Okay, then we have these two runtime boxes. Well, actually, we're at time now, but I don't know, we can either take more questions, or we could go quickly through those two boxes, or we can even stop now. I don't know, Kai, what's the best?
You have 2 more slides before the performance section. Because we've seen the charts in the performance section before.
Yeah.
Yesterday, maybe if you finish up those 2 slides, and then I think they may have lunch scheduled for us.
Oh,
I
okay.
mean, there's certainly lunch around here. I'm just trying to figure out where we go.
Maybe it's best not to delay lunch.
Well, if you can cover in 2 or 3 minutes. Is anyone ready to go
sure.
next? Okay.
So yeah, the runtime support basically covers like all the microkernels XLA might call, like TopK and library wrappers, and then runtime features like collective synchronization wrappers around the Nickel library, and then it provides a unified type of FI to register such microkernels easily with XLA. And then we have GTRT. I think this is like being actually evolved into a different system now. So this set of slides, I think, is already outdated. But at least as of right now, if you don't cover the evolution plans, it takes all these bits and pieces together from different kernels and glues it together into a single object file, which you can then serialize. You can store it to disk. You can use it for AUT computation. And if you link and run that object file, you can execute that GPU program. And that also inserts CUDA graphs in between the different fusions generated. And then this GTRT component right now generates this object file by compiling all the runtime code, but that actually incurs a non-trivial overhead, as we found out. So now we are trying to go back to the interpreted approach, where we would still have like a small interpreter launching kernels one by one, but it would use CUDA graphs and it would explicitly construct CUDA graph regions. performance charts I was told were shown already. I guess that's the most interesting one for training as driven by NVIDIA. And that's it. And then the closed source benchmarks we're busy optimizing.
Which might be worth jumping back to slide 63 for a second, just to show
Only I knew which one is 63.
two before this. There, that one. Because this is a graph I don't think that we saw before. It's actually demonstrating our performance, which is the blue bars on 7 billion, 33, and 65. This is Llama 1. Is that what that was taken from?
Yes, I believe so. So this is done by the PyTorch XLA team, which has launched the Llama 1 model on PyTorch through XLA. And another major focus for XLA this year is to improve PyTorch compatibility and to make such things easier with hopefully more results coming from the community.
Well, we're off to a good start, right? In this session, we've certainly seen all of the magic that happens within OpenXLA GPU. So if you get your HLO input in a good shape, we can work wonders with it, right? And it's only going to get better from here. So this is perhaps an illustration that even on a stack that we haven't invested as much in yet, but of course intend to, XLA can already do magic. Any more questions for George before we break for lunch?
Yes, I have one, John. Can you go back to the original slides for the XA architecture?
Well, I guess any one of them will do, right?
Yeah, this one. Yeah, I just wonder when you do the SDMD, SPMD partitions, would the hardware agnostic? Is it? I assume the TPU and GPU, the partition, the side of data side is different, or is it's completely hardware agnostic at that stage?
Yeah, it is mostly hardware agnostic. Now, it's conceivable to have something GPU specific if we find cases, but right now we have not found any cases. But yeah, it could be we have a subclass of this base SPMD partitioner. So you could add GPU specific logic there potentially, but right now it is mostly hardware agnostic.
But I guess like in optimizations, it gets GPU specific, like when you're trying to combine collectives or when you're trying to schedule, then it becomes very specific to hardware.
Okay. Thank you. So so I assumed which stage the way comes to concern the hardware configurations. So I think into the fusion stage, they will consider what kind of the hardware configuration you will take in consideration to make the decision.
Fusion is very hardware dependent, because when you fuse, you need to know the cost model, you need to know the compute cost, you need to know shared memory budget, you need to know number of registers you have. Well, number of registers we don't know, but like we do a best guess that if we fuse too much, sometimes we run out of registers and then it's terrible.
Okay. So before that, it's hardware economics. Okay. Thank you.
I mean, the way we stitch the passes together is still GPU specific. Like we have a GPU compiler, a different set of pass pipelines. So, there it is GPU specific. And then even within those, there are passes like a collective combiner, which are GPU specific. So I mean, yeah, so GPU specificity comes that way into the picture.
So I guess another thing to keep in mind, right? This is a high level overview. But there's a lot more passes that don't have their own boxes, right? So there's for SPMD partitioner, there's also like collectives optimizations. That's kind of subsumed here, right? As Rahul said, right? So there's even more kind of magic, but if you put all of that on the slides, it gets utterly confusing, right? So this is the high level view of the architecture, and there's lots more bits and pieces.
And one theme we're looking at is doing a bit of a pass cleanup. There are a lot of shared passes between GPU, CPU, and TPU. And it is difficult for some vendors to tell which ones are which. And it's just an overall effort to make this a little less prickly. stay tuned.
Yeah, actually, that was the exact question I was gonna ask. Like, since we share like some common passes, like it's XLA as a like community, like are we thinking to, have like a common device agnostic or CPU, GPU that we can use, like the common passes?
On the CPU side, we're definitely looking to have like the agnostic early library intercept cleanup passes more formalized and separated and defined. That's what we presented yesterday. And I think that's going to, as we have a little more headroom on GPU, we'll do something similar where we will have you won't have to basically dump out after each pass to figure out where you should go. That we don't want that anymore. That's too cumbersome, brittle, changes with the wind. So we're motivated by that same predictability. Right. We just haven't had time to do it, or we've had other bigger problems too.
Next year for sure. In fact, I said as much in my talk yesterday that we're committed to improving these things and reusing more passes, more code, more concepts from all over. The latency hiding scheduler that we covered originally came from, it was like two ideas simultaneously. One came from NVIDIA and one came from our colleagues on the TPU compiler team. And we realized there were some commonalities. Is that right? Rahul, roughly how it came from? Okay. So we'll do that more and more. These are good collaborations.
And also the pattern matching is basically, we're doing the GPU is doing the MHA fusion. We're also doing the CPU side, CPU fusion, but the pattern is same. So those kind of code can be shareable.
I agree. I think that's
Place.
a huge opportunity. Standardized, flexible, cross-platform pattern matching. Did I describe that right? It's a thing we can invest in.
And yet, to put a dose of reality, we are changing tires in a moving car in the sense that we can't afford to start over or make all passes like a box of Legos and do what you want. Like we do have some balance. So we.
Yeah, we also want to have incremental changes rather than drastic. Yeah, that makes sense.
Without getting stuck in local minimum that sucks. So.
Terrific. Any more questions for George? Okay, George, thank you very much. It's 9 p.m. your time in Zurich. Thank you. Thanks for staying late.
Thank you. Yes, thank you for your time.
Catch you later. Thanks.
Thanks, bye.
Oh, okay. Yes.